Hello, this is Jude Socrates, and today's video is about lines and planes in R3. So in our last two videos, we were looking at the span of a set of vectors. And we said that if you have a single non-zero vector, then the span of that vector is what we call a line, whether you are in R2 or in R3. But if you have two vectors and they're not parallel to each other, we saw that in R2, they will span the entire Cartesian plane R2. But if you're in R3, then the span of those two non-parallel vectors is called a plane in R3. So we saw that we can write the equation of a line in R3 in three ways. We have the vector form, we have parametric equations, and we have symmetric equations. But for planes, we found a Cartesian equation for our plane. And also remember that in both lines and planes, the examples that we saw pass through the origin. And that's because the span of a set of vectors always contain the zero vector. So far, the lines and the planes that we have seen, whether in R2 or R3, they pass through the origin. So now we're going to create lines and planes which possibly don't pass through the origin. So let's start off with lines in Cartesian space. We know that if you take any 2 points on the plane, you can take something like a ruler and connect those 2 points with a straight line. Well, there's nothing stopping us from doing that in Cartesian space as well. So we will adapt Euclid's axiom for a line and say that through any two distinct points P and Q, we can draw a line segment PQ using a ruler or a straight edge, whether that's on a plane or in space. And we can extend this line segment PQ infinitely in both directions, and we will call that the line PQ. So in the first notation, we have a short line segment above PQ, indicating it's a line segment. And then we have double-headed arrows above PQ that indicates that it's a line. Okay, so let's make an example. Consider the line in R3 that passes through the points P, 4, minus 1, 5, and Q, 2, 5, 6. So let's go to GeoGebra and take a look at these 2 points and make the line that goes between them. So here's our homepage for GeoGebra. And remember, we have to go to 3D graphics. And let's again grab our system and spin it around so that the positive X direction is to our left, positive Y to our right, positive Z is always pointing upwards. So we're going to input our 2 points. Let's call them P will be the point. All you need is a pair of parentheses. So we have 4, minus 1, 5, and Q will be the point 2, 5, 6. All right, so there they are. And you can change the size of the dots representing P and Q if you want to in the settings, but they're fine for now. So what we're going to do is we're going to make GeoGebra draw the line for us. Now, I mentioned on the first time that we saw GeoGebra, there are some icons here that we'll talk about later. Well, this icon makes lines for us, okay? So what you have to do is click on one of the points and then click on the other point, and there's our line. So see how GeoGebra automatically made an equation for us. And we have 4, minus 1, 5. And yeah, that's our first point, 4, minus 1, 5. But we have this plus lambda minus 2, 6, 1. Well, I see 2, 5, 6. What is this minus 2, 6, 1? Well, it could either mean a point or a vector. The trouble with GeoGebra is that it can take it one way or the other. All right, so sometimes you have to be particular about how you want to treat a point or a vector. Okay, so let's see if it's a point. What does minus 2, 6, 1 look like? Okay, there's that point right over there. We have a new blue dot in space. Maybe it's a vector. So let's call it D. D is the vector minus 2, 6, 1. So remember, you have to make an extra pair of parentheses inside. Aha! So of course the vector D is pointing at the point A, because the endpoint of D, of course, is the point A. So is that a more meaningful interpretation of this minus 2, 6, 1? So let's spin our diagram around and see. Ooh, yes. Check out the relationship between D and that line that we want. Ooh. Don't you think that the correct word in this case is parallel, right? That vector D looks like it's parallel to the line that we want. And of course, there's a reason why I picked the letter D to label this vector, and it's because it's a direction vector. So we saw in our, I believe, first video that we had the span of a set of vectors, and that single non-zero vector that we started out with, we said we can call that the direction vector of our line. Okay? But notice here that the direction vector is not on the line. Okay? So we still have a little bit of work to do. So as I said earlier, one of our goals is to create equations for these lines in space. We want a vector equation, parametric equations, and symmetric equations. So let's think of this line in terms of vectors, right? Let's start at the origin. How are we going to get to a point on this line? Well, one way to do it is go to the point P, and then from P, follow this direction vector as far as you want to. In other words, you can go by D itself, or maybe you can go by twice D, or maybe you can go in the opposite direction. You can go minus D. So think of it as the vector from the origin to P plus a multiple of this direction, D. All right, so here we are back in Scientific Notebook. So our goal is to make a vector form, a parametric form, and the symmetric form for the equation of this line. And we said that our first step is to think of going from the origin to P, and so we will turn P into a vector. So instead of round parentheses, we have our brackets, our vector brackets. So now we need the direction vector from P to Q, right? So how do we do that? So remember, what that means is you subtract the coordinates of P from the corresponding coordinates of Q. So we have 2 minus 4. 2 minus 4 is negative 2. And then we have 5 minus negative 1. So that's positive 6. And then we have 6 minus 5. So that is positive 1. So that is our direction vector. Okay? So what is the vector form for this line? You go to the point P from the origin. So that's the vector 4 minus 1, 5. And then you add any multiple that you want of this direction vector. So plus T times the direction vector minus 2, 6, 1, whereas before, T is any real number. All right, so that's our vector form for the line. For the parametric form, just find each coordinate. So for x, you get 4 minus 2p. And for y, you get negative 1 plus 6t. And for z, you get 5 plus t. There we go. So in our first video, we didn't have the 4, minus 1, and 5. It was just minus 2t, 6t, and t, for example. Okay? So for the symmetric form, remember that we will solve for t from each of these equations. So we will get x minus 4 divided by negative 2 from the first equation. And then from the second, we'll get y plus 1 over 6. And then finally, you have z minus 5 over 1. Oh, okay, so we don't need the fraction. We can just write it as z minus 5. So when you see this, let's say on a homework problem, and oh, well, there's no denominator. That denominator is simply 1. Okay, so what we're going to do next is go back to GeoGebra, and I'm going to show you how to use the vector form of this line to draw the line without using that command that we saw in GeoGebra. Okay, so here we are. So let me hide this line. So all you have to do is click on this circle, and that entry disappears. So the new command I'm going to show you is the curve command. Okay, and you might say, well, we're drawing a line. The line doesn't curve. Well, a line is an example of a curve. So notice it says expression, parameter, variable, start, value, and value. And here there are 3 expressions. So one of them is for a curve on the plane, 2-dimensional view. And the one we want, of course, is the 3-dimensional view. Okay? So the expressions that we're going to fill in here are the expressions for x, y, and z. Our parameter is t. Starting value, we can go from, let's say, negative 3 to positive 3. Let's see if that fits. So in our vector equation, we will have 4 minus 2t, and then we have negative 1 plus 6t, and finally 5 plus t. Our parameter is t. Let's go, how about from minus 2 to 2? See, there it is. And of course, that looks pretty much like the same line that this command drew for us. So let's generalize what we just did. If you had these 2 distinct points in Cartesian space with coordinates a1, b1, c1, and a2, b2, c2, how will you find the unique line L passing through P and Q? So first you create the vector from P to Q, and you take the difference. So you have a2 minus a1, b2 minus b1, and c2 minus c1. That's the direction vector of your line. A point xyz is on the line L if and only if the corresponding vector xyz satisfies the vector equation for L. So xyz is the vector from the origin to P plus any multiple of the direction vector. So again, you turn P, a point, into a vector, a1, b1, c1, plus all multiples of this direction vector. So we can also think of it as this line L is a translate of span D, which we saw in our first video. Span D will pass through the origin, but if we move every vector in span D by the vector a1, b1, c1, then we get a line which may not pass through the origin. So how about the 2 other forms? So from the vector equation, which we can just write simply as x0, y0, z0 plus t times abc, we can get the parametric equations. So again, solve for x. X is just x0 plus t times a, or a times t. Y is y0 plus b times t, and z is z0 plus c times t. Now, how do you solve for t? Well, it's possible if none of these coefficients, a, b, and c, is 0. In that case, you will get t is x minus x0 over a, y minus y0 over b, or z minus z0 over c. Set them all equal to each other, and you get the symmetric equations for our lines. Let's also talk about parallel lines. So we can think of d as a direction vector for our line. So you can have several lines that have the same direction vector. And of course, a good way to think of that is that they're parallel to each other. So two lines L1 and L2 are parallel to each other if they are distinct translates of the same line through the origin. So in other words, they have no point in common. So L1 and L2 are parallel if and only if their vector equations can be written using the same direction vector d. Remember that the direction vector is not unique. You can multiply it by 2, by -3, and it's still a direction vector. But if two lines are parallel, you can write their equations using the same direction vector. But to guarantee that they don't have a point in common, you have to guarantee that x1 minus x2 is not parallel to d. If they are parallel, then they're actually the same line. Okay, so now let's continue with planes in R3. We saw when we have two non-parallel vectors in space that they will span a plane, and we found the Cartesian equation for that plane. So Euclid also told us something similar, that if you have three distinct non-collinear points in Cartesian space, so what does that mean? The line PQ does not contain the third point R. Then there's a unique infinite plane, capital Pi, that contains all 3 points PQ and R. So in other words, any triangle in space is contained in a unique plane. So let's look at these 3 points. We have 3 minus 4, 2, 2 minus 1 minus 3, and minus 2, 5, 1. So let's start a new version of GeoGebra, plot these 3 points, and we're going to study the plane that contains all 3 of them. All right, there we go. So I've gone ahead and input our 3 points, P, Q, and R. And let's turn this around and see, yeah, there are the 3 points. And of course, they form a triangle. They're not all on the same line. So we want to create the plane that contains these 3 points, okay? So how are we going to do that? Well, let's think about what we did when we had 2 non-parallel vectors, right? Can we think of these points as forming vectors? Well, we can make the vector from P to Q and the vector from P to R, okay? So in other words, think of P as the origin and then make a vector to each of these other 2 points, okay? So I can use GeoGebra to make our vectors for us. Notice that when you type vector, it gives you the choice of putting in a start point and an end point, okay? Since we already labeled our points, all we have to do is type in vector P, comma, Q. Okay, so you can see there, that's the vector from P to Q. And similarly, we can make the vector from P to R. All right. So there's our second vector. So if we're back 2 videos ago, we could have taken all the linear combinations of these 2 vectors, and we will have a plane that passes through the origin. Okay, does this plane pass through the origin? Well, let's turn it around. And no, I don't think so. If there were a plane containing all 3 points, it would have to look like this, and it doesn't look like it passes through the origin. So of course, something different is happening now. Okay, so when we did the line, we said one way to make that line is to go from the origin to P and then follow any scalar multiple of that direction vector that we found, okay? we have two vectors here now, the u and the v. Okay, so what are we going to do? Well, fortunately, GeoGebra also has another command that will help us. So that command is called surface. Okay, so notice, this is what we want. We have expression, 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 kind of like curve, except we have parameter value, variable 1, start value and value, and another one for parameter variable 2. Okay, so that's because we have these two vectors that are going to help us. So here's what I'm going to type. Surface, parenthesis, I will take capital P plus R times U plus S times V. Okay, so I'm treating the point P as a vector, and I'm adding a linear combination of these two vectors. So who are these R and S? R will go from, how about negative 0.5 to positive 1.5, and S will go from negative 0.5 to positive 1.5. Ooh, so there it is. So there is our surface. And I also didn't show you, you can use the wheel on your mouse to zoom in and out. So here we go, zooming out so we can see. Ooh, check it out. So there is what looks like a plane, doesn't it? And it contains those 3 points, P, Q, and R. It's almost like we're in a flight simulator. Okay, try not to get dizzy. Okay, so let's generalize what we just did. We have these 3 points, and we made two vectors, u and v. So we connected P to Q and P to R. And then we said, okay, let's make this surface. Okay, this command surface that we saw in GeoGebra. And of course, this is exactly the same idea that we need to create an equation for the plane. Eventually, we're going to get a Cartesian equation for the plane. But the first time we did this, we said that x, y, z would just be a linear combination of the two vectors, u and v. Now we have a1, b1, c1 coming from the point P. So we can call this also a vector equation for the plane. So we have xyz equals the point P1 turned into a vector plus a linear combination r times u plus s times v. And of course, we can also think of this also as a translate of the plane span uv, which passes through the origin. We will take that plane and we're translating it by the constant vector a1, b1, c1. Okay, so let's do the algebra on our example. So we want the vector u from P to Q, and that will be 2 minus 3, which is negative 1, minus 1 plus 4, which is positive 3, and minus 3 minus 2, which is minus 5. Okay, and from P to R, we have minus 2 minus 3, which is minus 5, and then 5 plus 4, so that is 9, and 1 minus 2, that would be negative 1. Okay, so now we can make our vector equation. xyz is turn P into a vector. So I will make a copy of this and just copy 3 minus 4, 2, and then add any multiple r of the first vector plus any multiple s of the second vector. So this should remind you a lot of that time when we only had the span of two vectors, and the equation was exactly the same, except it looked like this. So now we have P turned into a vector plus the linear combination of our two vectors PQ and PR. Okay, so now our next goal is to transform this vector equation into a Cartesian equation for the plane. So last time we got something like ax plus by plus cz equals 0, but of course we don't expect the right side to be 0 anymore because our plane doesn't pass through the origin. If x, y, and z are all 0, you will get 0. That doesn't happen in our case. Now, when we did this last time, we said that the first thing we're going to say is that if there is a solution R and S to this equation, that solution had to be unique. So remember, we said if this is this plus R1 times this plus S1 times this, and it's also this plus R2 of this plus S2 of this, and we subtracted the two sides, and we got that these two vectors would be parallel to each other. Okay? Again, these two vectors are not parallel to each other because we have a triangle. So those two vectors can't be pointing in the same direction. So it's the same thing here. If we do have a point on this plane, then there's exactly one value for R and one value for S that will create that vector as a linear combination plus this extra vector. So let's go ahead now to the main event, okay? We find every coordinate. We get x is 3 minus r minus 5s. Y is minus 4 plus 3r plus 9s. And z is 2 minus 5r minus s. So again, we get three equations in two variables, and it's almost like what we saw last time, except we didn't have the 3 and the minus 4 and the 2. So again, we're going to use the addition method to eliminate either r or s. Well, I think we did eliminated r last time to get s. So now, because we have that minus s here, let's eliminate s this time around. Okay, so here are our three original equations. To eliminate the minus 5s, we will multiply the equation for z by negative 5 to make positive 5s. So we will get minus 5z minus 10 plus 25r. Okay, so now for the 9s, we have to multiply the third equation by 9. So we get 9z, 18, minus 45, and the minus 9s. Okay, so the next thing we're going to do is we're going to add this equation to the third equation and this equation to the third equation. Okay, so we have x minus 5z is equal to 3 minus 10, negative 7, and minus r plus 25r is 24r. Okay, and now for this one, we have y plus 9z equals minus 4 plus 18, that's 14, and 3r minus 45r, we get minus 42r. Okay, so our next step is to solve for r from both equations. So we will get the fractions x minus 5z plus 7 divided by 24 is our r, and it is also the fraction y plus 9z minus 14 divided by negative 42. Okay, and then we will cross multiply, so we will get negative 42 times this numerator on the left, cross multiplying, equals positive 24 times the numerator on the right. So we can ignore the r. Okay, now notice that 42 and 24 are both divisible by 6. So we can make these equations a little bit simpler. Divide them both by 6, so we will get negative 7 and positive 4. Okay, so the numbers are a little bit smaller, and now we can expand. Negative 7x plus 35z minus 49 equals 4y plus 36z minus 56. Okay, so we have a single x, a single y. We have two z's over here. So how about let's move all the variables to the right, because minus 7x will look better as positive 7x, plus 4y looks great by itself, and 36z minus 35z, that's just one z, and we can put the minus 56 on the left. So we get 56 minus 49, I believe that is 7. Okay, so there you have it. That is the Cartesian equation of our plane. And if you want to make it look nicer, you can of course put the variables on the left and the 7 on the right. Yay, mission accomplished. So I'm taking you back here to GeoGebra to show you that the plane that we got is indeed correct. So you've seen this command before, 7x plus 4y plus z. Before it was 0, but this time on the right we will have 7. Ooh, so there is our fuzzy plane. And is it the same as that surface that we got earlier? Yep, there it is. Yep, there's your edge view, and it does look like our plane is correct. All right, so we have two ways to generate the plane that contains those 3 points. Okay, so before we go, let's summarize what we did. If you have 3 non-collinear points P, Q, and R, you can create a Cartesian equation for the plane that contains those 3 points. And it has the form ax plus by plus cz equals d. And of course, not all of the coefficients a, b, and c are 0. The plane passes through the origin if and only if the right side of that equation is 0. Now, as before, we don't call this the Cartesian equation. We call it a Cartesian equation because it's not unique. You can multiply both sides of the equation by the same non-zero constant k, and you will get an equivalent equation for the plane. So we can also think of parallel planes. They can be written with the same coefficients. So the left side will be the same, ax plus by plus cz. But on the right side, you will have different constants. So on the right side of pi 1, you will get d1. And on the left side of pi 2, you will get d2. So those planes will be parallel if the right sides are not the same. If they're the same, of course, you have 2 identical planes. All right, so we have reached the end of our video. You will find me on Facebook. You will find the 4th edition on Facebook, and also, of course, on kendallhunt.com. So until our next video, thank you very much for watching. Goodbye.